In the first module, we considered why writing clean code is so important. In this module, we'll explore 3 important clean code principles. Let's get started. Okay, pay attention, because throughout this course, you're going to hear regular references to these 3 core principles for writing clean code. First, clean code involves using the right tool. As software developers, we have so many tools at our disposal that sometimes the hardest part is simply selecting the right tool for the job. We have to recognize that every technology has its place. Throughout this course, we'll discuss how to select data structures, when certain technologies become evil, and outline some places where you can avoid writing any code at all. Secondly, we're going to talk about the signal-to-noise ratio of our code. In science and engineering, the term signal-to-noise ratio compares the level of a desired signal to the level of background noise. A quality audio amplifier produces minimal noise as it boosts sound, which allows the listener to enjoy the music without creating distracting background hiss. In the same way, clean code optimizes for signal and strives to remove any noise so that the reader can easily read the logic and understand the intent. We'll walk through many techniques for increasing signal and eliminating noise from our code. Once we've selected the right tool and optimized our signal and removed noise, our lofty goal is to write code in such a clear and expressive style that no documentation is needed at all. Code that reaches this level is self-documenting. Steve McConnell, author of Code Complete, points out that the main contributor to code-level documentation isn't comments, but good programming style. We'll walk through many techniques for replacing comments and other developer-oriented documentation with expressive code. Now let's review these 3 principles in more detail. Okay, be honest, you've probably worked with somebody that has this sort of mindset. Sure, many developers have a few favorite technologies, and there's nothing wrong with specializing and striving for expertise with a given tool. But make sure this line doesn't apply to you. Developers who become too fixated on a given tool, pattern, or paradigm are cursed to misuse it. Like this. Yes, sadly, this is me hauling furniture. Clearly, my grocery getter is the wrong tool for this job. Now, here's the funny thing. I may walk around with pride and expect you to compliment me on being a creative problem solver. I took something that was clearly not going to fit and I hacked in a solution. As developers, we do this all the time. In fact, I could go on and I could brag about how I put padding on my armrest to keep the heavy box from scarring up the interior, and I closed the sunroof the perfect amount to provide extra support on the box so that it doesn't fly out when I drive down the highway. And hey, the rain hardly leaked in through the opening in the sunroof. Now, at this point in real life, you'd be holding back an epic eye roll, because this work is nothing to be proud of. It's hard to even sit in the driver's seat and work with the steering wheel with the box sitting there, and I can't even use the rearview mirror. My mistake, quite clearly, is I began by selecting the wrong tool. So what does this look like in programming? Well, here's a great example. Using regex to validate an email. Sure, regex is useful, but the email specification is surprisingly complex. So if you need to validate an email comprehensively, regex is probably the wrong tool for the job. Reading or modifying a regex that's this complex would be a huge challenge. We need to break this problem down into well-named pieces, and a single regex does not make that easy. Next, let's explore some principles for selecting the right tool for the job to avoid mistakes like this. When selecting tools, the risk for picking the wrong tool for the job exists at the boundaries. Let's consider some common technologies for building web applications today. Each technology has a specific purpose. HTML provides semantic markup for our content. CSS separates our styling from our markup. JavaScript provides behavior, and the server-side language that we choose manages the business logic. Finally, SQL is useful for relational database, data access, and manipulation. And here's the thing. It's the boundaries and interactions between these technologies that get people in trouble. First, It's tempting to put HTML in a JavaScript string so that you can dynamically inject HTML onto the page, but all markup should ideally be written as HTML. JavaScript is the wrong tool for storing markup. And on the flip side, it's tempting to put JavaScript directly in your HTML, but this mixes concerns by injecting behavior directly into your markup, and it eliminates the opportunity for caching and reuse. When possible, JavaScript belongs in .js files and HTML belongs in .html files. Second, generally relational databases should contain raw normalized data so that it can be leveraged for a variety of purposes. Thus, storing HTML in the database or injecting HTML and query results as strings is problematic. It binds the presentation and data storage together, which makes reuse really difficult. It's a very similar story with the HTML-CSS interaction. It's tempting to place styles inline in HTML, but this mixes our semantic markup with style. These are separate concerns, which eliminates the opportunity for caching and reuse of CSS. It's easy to create highly dynamic SQL in a server-side language like C# using strings to generate SQL statements, but stored procedures and ORMs often provide a safer and more elegant approach to generating dynamic SQL. Finally, this is the most common tool misuse that I see, using a server-side language to generate dynamic JavaScript. In most cases, JavaScript can remain in a JS file, and JSON can be returned from the server to provide dynamism. Let's now take a look at a specific example of using the wrong tool for the job to generate dynamic JavaScript. Here we have an example application that is delivering the Google Analytics JavaScript code dynamically. As you can see, the Google Analytics ID is being injected into the middle of this script. So this is a snippet of code that would sit in C#, for instance, within a code behind. And the idea was that we'd put it within a string so that we could inject the one dynamic piece here, which is the Google Analytics ID. Now let's take a look at a cleaner example. Here we can see that the JavaScript code is now sitting within a file called googleanalytics.js. And we can also notice right away that we have the benefit of code coloring, which makes the code much easier to read. And imagine if I made a typo along the way, I'd know immediately. If I typo up top and type document and miss the U, I wouldn't know this until I ran the code. But my IDE will help me out as I write within a JS file using the style below. Now you're probably wondering, where is this website setup.googleanalytics key defined? Well, it's defined in the header of the document. Here we can see a snippet of JavaScript that defines this data. And the beauty of all this is all just native JavaScript. To inject this dynamic data into the header, you can use your language's JSON serializer to serialize some native object. In this case, I'm using C#, so I can use C#'s JSON serializer to serialize this out into the header so that I get this dynamic piece of data that's useful for my JS file down below. And there's a lot of benefits to doing so. By staying native, our code is cached. It's downloaded once by the browser, and then that JS file isn't requested again because it already has those resources. When you put JS within your HTML, it's downloaded again and again on each page request. It's also code colored. If you looked at the old version in a string, it was all code colored as the one C# string, which makes it very difficult to read and maintain. Closely related to this, you lose syntax checking when you try to write one language within a string. There's no way for it to check whether you've made a typo, so it becomes very difficult to maintain. Separate files for each language are easier to maintain and understand because each file handles a single focused role, and we wouldn't have any easy way to reuse this code. This is also more performant because it avoids string parsing on every single request. Instead, we serve up the file once, and then browsers in a lot of cases don't request it again for a long period of time. Finally, we can minify and obfuscate our JavaScript code in this case because it's a separate file. That wouldn't be easily done if we were doing string parsing and building this together dynamically. Of course, the importance of staying native isn't at all specific to JavaScript. There's a variety of opportunities to find yourself struggling with strings when there's a less painful alternative that involves staying native. The bottom line is, avoid using one language to write another language or format via strings. Creation of these formats dynamically is a solved problem in most popular languages these days, so be sure to leverage libraries to generate such formats. A good rule of thumb is to strive for one language per file. Generating any of these items via strings requires the reader to understand the interactions of two technologies simultaneously. And as we just saw, this totally breaks tooling support. So, if you notice you have two languages in one file, think twice about how you could eliminate one by solving the problem in a different and more elegant way. Every technology has its niche and its limits. The trick to choosing the right tool for the job involves considering when the technologies that you know best have become evil. Let's consider some examples. LINQ to SQL is a powerful and loved technology for data access used by many C# programmers. However, it becomes ungainly when used for massive queries and has an obscure syntax for simple outer joins. SQL is useful for querying the database, but queries should not embed display logic. And as we just saw, C# shouldn't typically be used to write JavaScript and HTML in strings. So before we reach for a technology, we have to ask, are we using it in the right way? The second clean code principle is to maximize the signal-to-noise ratio. To enjoy good music, signal-to-noise ratio is a key factor. If there's too much noise, it's hard to understand the lyrics. The more subtle pieces of the music are lost, and the whole experience becomes less enjoyable and more taxing. In the same way, code with a high signal-to-noise ratio is easier to understand. In this course, we'll define signal as any logic that follows the TED rule. TED stands for terse. Your code should not be excessively wordy. Expressive. It's clear what the code is trying to do. And finally, the code should do one thing. It should have a clear responsibility, and it should do that one thing well. But in competition with signal, there's always noise. So throughout this course, we'll walk through items that add noise to our code and discuss techniques for increasing the signal and reducing noise. This is just a sampling of some common items that add noise to our code and thereby reduce readability and hinder maintenance. When we read code, our brain is the compiler. A 1956 study published in Psychological Review found humans can hold no more than 7 items in short-term memory at once, plus or minus 2. Thus, having more than 7 items in scope at one time makes it difficult for the reader to comprehend the code. The rule of 7 has a big impact on how we should write code, including the number of parameters we should accept for a method, the number of methods in a class, and the number of local variables we keep in scope at a single point in time. Methods with more than 7 parameters are certainly difficult to reason about. To assure that humans can read and reason about our code, we must strive to break it down into bite-sized pieces that we can hold in our head. Second, the signal naturally decays over time and noise naturally grows over time. So we must refactor regularly as we write and maintain our code to avoid creating a huge mess that needs to be replaced rather than maintained. This kitchen didn't become a disaster overnight. Day by day, no thought was given to organization. No time was taken to clean up before starting the next task. Trash wasn't thrown away. In a condition like this, it's very difficult to do even simple tasks like cook bacon and eggs. In the same way, if we don't regularly strive to write clean code, we may find ourselves here. This is a massive SQL query from the Daily WTF. It's called the Query of Despair. Just like the kitchen, this query didn't become an intimidating mess in a single sitting. It's the product of ongoing changes without concern for writing clean code, and no refactoring was done along the way. The computer has no problem parsing this, but our finite brains overflow attempting to parse something so complex. Arguably the most important principle in programming is don't repeat yourself. Or, as the book The Pragmatic Programmer called it, The dry principle. Clean code honors the dry principle by stating each piece of knowledge or logic once and only once. Relational database schema designers normalize their database in an effort to assure each piece of data is defined in a single place. This assures that the database operates efficiently and consistently and eases maintenance. This principle holds true in code as well. Copy and paste is often a sign of a design problem and can easily be eliminated by creating a reusable function or adding a parameter to an existing function to make it more flexible. Now, there's a number of issues with duplicated code. If code is copy and pasted into multiple locations, it decreases the signal-to-noise ratio. It's the equivalent of repeating the same paragraph twice in a book. Authors get their point across once and make references to previous chapters. Methods and classes serve the same purpose in object-oriented programming. Clean coders strive to avoid copy and paste since every line of code is a liability. It's code we have to maintain. It's code we have to read. It's code we have to debug. Bill Gates said, measuring programming progress by lines of code is like measuring aircraft building progress by weight. So true. Much like an airplane, our goal is to stay light. This means minimizing the lines of code in our codebase. And multiple studies have found that fewer lines of code are correlated with fewer bugs. This duplication also creates a maintenance problem. When a bug is fixed in one spot, it may persist elsewhere. When a feature is added in one place, other copy and pasted locations are likely to be overlooked. And keep in mind that many pieces of duplication aren't even immediately obvious. But if you squint your eyes at this code, you can see that it has a repetitious shape. And this infers that there's an opportunity for simplification. Keep an eye out for shapes and patterns as you code to sniff out subtle cases of redundancy. The third principle is clean code should be self-documenting. Programming style as documentation is all about writing code in such an expressive and clear style that the author's intent is obvious. So obvious that new developers joining the team can easily navigate and read the code to get up to speed. This is a key concern as outlined in a study by Felstad and Hamlin in 1979, which found understanding the original programmer's intent is the most difficult problem. Any maintenance programmer can attest to the fact that often the hardest part of the job is figuring out what the original programmer meant to do. Self-documenting code strives to do 4 core things. First, express intent clearly, so that readers understand exactly what the programmer was trying to accomplish. Second, layers of abstraction should be used so that the problem domain can be considered and walked through at different levels of detail. Third, formatting in a friendly and consistent manner will optimize the reading experience. And finally, favoring code over comments when possible will assure that the code is as expressive as it can be without relying on comments to explain away unnecessary ambiguity. Self-documenting code can reduce and ideally eliminate the need for out-of-band documentation, such as JavaDoc, wikis, etc., by clearly expressing desired behavior within code instead. In this module, we explored 3 clean coding principles. First, use the right tool for the job. As I showed in the regular expression email, if we pick the wrong tool, then clean coding isn't going to help us much at all. Boundaries matter. Watch for the seams between technologies. That's often where we end up using the wrong tool. Stay native. Avoid using C# to generate another language. Use libraries to generate other formats instead. To help enforce this, it's typically a good sign to have one language per file. The second rule was to maximize the signal-to-noise ratio so that your fellow developers aren't distracted by needless extra text and code. Write code that follows the TED principle. It's terse, yet expressive, and it does one thing. Try to keep your code dry. Don't repeat yourself. Watch for repeated patterns. This can be a sign of duplication. The third and final rule was to strive for self-documenting code.
As we'll see, this isn't always possible, but we'll see a variety of approaches for getting there. In the next module, we'll discuss a key factor in writing clean code. Let's discuss naming.